Okay, try this again. We are doing the third section of chapter 24, the Earth, Moon, Sun chapter. So today we're doing the sun. Really? Sorry, craziness. Today we are going to talk about the sun. By the time we are done, you should be able to describe the layers of the sun. There are 6 layers that we're going to talk about today. And some of the surface features of the sun. I think there's only 3 that we're talking about today. Maybe 4, but I think it's 3. So, if I took the mass of all of the planets, of all of the moons, of all of the everything in our solar system, and I added them all together, that would only make up 0.2 of 1% of the total mass of our solar system. I'm adding everything together except the sun. The sun's all by itself. But I'm adding, all of our planets, all of our moons, all of our satellites, everything in our planet or in our solar system, adding the masses of those together. That's only 0.2 of 1%, not even a whole percent. So that means that our sun is absolutely ridiculously bigger than everything else, right? It makes up 99.8% of all of the mass in our solar system. That's how much bigger it is than all of everything else. Okay? Hopefully by now. The sun is kind of the center of our solar system. It is what everything rotates and revolves around. It is the largest object in our solar system. Again, you probably at this point kind of want to go, duh, it makes up 99.8% of all the mass. Hopefully that means it's the largest thing. And it provides all the light, heat, and energy that we need on our planet in order for life to survive. Anybody surprised by any of that today? Good, I'm glad. I don't know what my mask is doing today. I have to switch it out. Okay. Are we good? So, we've talked about gravity like all over the place all the time since we started talking about anything about space. It's all about gravity. And it's gravity that holds the sun and pulls it into that spherical shape. Just like it was gravity that made us into a sphere, and the gravity that made the moon into a sphere, and gravity that made all the other planets when we get them into spheres. Well, guess what? It did the same thing to the sun. Okay, pulls it, makes it into a sphere. Now, I am surprised at the number of people in the last several days who have come and asked me, is the sun solid? The answer to that is no. The sun is not a solid planet like we are. The sun is made up of helium and hydrogen, both gases. Remember those? Remember having the periodic table? Do you guys remember seeing the periodic table? Helium is on one side and hydrogen is on the other. One of them has 1 proton and 1 neutron and one proton and 1 electron, and one of them has 2 protons and 2 electrons. Right? Again, it is not a solid, but here's the weird thing. It's not really a gas either. It's kind of that weird in-between place called plasma. Sorry. Plasma, basically it's a superheated gas. It doesn't really act like a gas, but it doesn't really act like a solid, and it definitely is not a liquid. So it's really, that is, by the way, plasma is the fourth state of matter. Okay? We talked about that forever ago, so you may or may not remember that. So, 6 layers of the sun. We're going to start in the middle like we always do and work our way out, right? So here, ready? What has been at the center of every planet that we've talked about so far? A core. Hot diggity. Well, guess what? The sun has one too. What? Yeah, it does. It doesn't have an outer boundary though, right? Yeah, I forgot we don't start with the core. I forgot we start. Sorry. Doesn't have an outer boundary, but it does have those specific layers on the inside. I forgot I said that first. I only made this last night. Come on. There, see, I told you it was on this slide. The innermost one is the core. Skipper. Not here today. Bye. The core is a little bit warm. Just a little bit. 48,600,000 degrees Fahrenheit. And at that temperature, hydrogen little molecules are so excited and they're moving around so fast that they smash into each other. And when they smash into each other, they combine. Okay? That's called nuclear fusion. And nuclear fusion gives off a heck of a lot of energy. Okay? That amount of energy doesn't just stay down there at the core. It's got to go somewhere. Because energy never just sits still. Anybody ever know anybody who is hyper? Right? Or are you that kid? I was that kid. Oh. Only mine wasn't, I didn't move around a lot. You will be shocked to hear, I am sure, that I could not keep my mouth shut. I know, you're all shocked by that, right? What? Mrs. Skipper, you couldn't be quiet? No! I know. I hide it really well, because I am so shy. I can't even say that without laughing. Okay, the next layer out. So we got the core. That's where all the action is really taking place. That's where we're making the energy. We move out from that, and the temperature drops. Did you see that? Temperature dropped like big time. This is only 12,600,000. Like we're on vacation. Okay, this is the radiative zone. Now, this is the weird part. Because it doesn't look that big, and so a lot of people think that the energy just moves really fast through all these zones, and it's created down here, and then poof, it's out at the top, right? But that's not what happens. What happens is, in the radiative zone, little teeny tiny light particles, they're called photons. That's what's created. Okay? These little teeny tiny light particles start moving around. Now, the thing is, there's so many of them, they can't go very far before they bump into each other. they bump into each other, they don't just bump into each other and bounce off and go on. They bump into each other and their energy absorbs each other. And then they kind of hang out for a minute. You know, it's kind of like you guys in the hallway. You know, you can't just walk from one class to the next one, right? You have to walk for a little bit and then you stop and you talk to whoever you're next to, or you bump into somebody that you know. And so you stop and talk, and then a little bit later you move on, and then, oh, TJ, how's it going, man? You doing okay? And then you stand there and talk to TJ for a minute. And then it's like, oh, hey, Tyler, did you hear about what happened last night, right? And instead of being able to walk the 30 feet from class to class, and, you know, in like 30 seconds, it takes you the whole 5 minutes to get there. Well, that's what happens with this. Miss Brenda upstairs called for you. You know who I'm talking about? Just go ahead and take it. You know who I'm talking about?
Yeah.
Okay.
I'm already sweating.
All right. So they just keep bumping into each other, absorbing and then releasing. Bumping into each other, absorbing and releasing. And this is like a millimeter. You guys, you know millimeters are like this much, right? Okay. So it can take up to 50 million years to go from the core to the outside of the radiated zone. Because they're always bumping into each other, hanging out, moving. Bumping into each other, hanging out, moving. Bumping into each other, hanging out, moving. Bumping into each other. Are you getting the drift here? 50 million years. Crazy. Crazy. When they finally come to the end of the radiative zone, they have hit the convective zone. This is the last layer of what is considered the interior of the sun. Convective zone, we've already talked about convection currents like 500 times. Some of you are going, oh yeah, I remember those. This is the good part. And others of you going, convective zones? We talked about convection currents. What are you talking about? I'm telling you. Convective zone begins at the end of the radiative zone and goes all the way up to, it says the sun's surface, but the sun doesn't really have a surface. So it's basically, it's really the first layer of the sun's atmosphere, okay? So it is the last, like I said, considered the last interior layer. So here we go. Hot material close to the core, close to that radiative zone. It's hot, so it rises, right? Because hot things rise, right? Oh, come on, y'all. I know it's first period, but hot things rise, right? Yeah. Okay. So that hot material down here close to the radiative zone, it's really, really hot, so it starts to rise because it's less dense. And as it rises, it goes. As it rises, it starts to cool, just like we do when we're at a bonfire. When we're close to the bonfire, we get hot and toasty. So what do? Step away. And the farther you get away from that bonfire, the colder you get, right? Until finally you're standing out here going, what am I doing? Back down to the bonfire. So that's what it does. Hot material moves away from the heat, the source at the heat source at the core, and it starts to cool down until it reaches again, it's the surface, it's the top part of the interior, rises until it reaches that, and then it starts getting really cold, and as it really cools down, it goes, oh, too cold, and sinks back down into the radiative zone. because cold stuff sinks. Hot stuff rises, cold stuff sinks. That is a convection current. And then it gets back down by the radiative zone and it heats up again and it rises and it gets up close to the surface and it gets cold and it sinks and it gets back up. Keeps going around and around. This is partially why we have two of the features we're going to talk about in a little bit, sunspots and solar flares. Are you good? Hi. So the last three layers aren't they're much more gaseous. Okay? They're considered the sun's atmosphere, not the internal part anymore. And the first one of those, I forget what I put in here, sorry. Remember, no solid layers, because the sun is not solid. So there are no solid layers. So the areas between these are really fuzzy. If you look at this, I loved this picture when I found it. You should have seen me trying to look for a picture of this. But I love this picture when I found it because you can see how there's a boundary here, but it's kind of fuzzy, and there's definitely a bunch of fuzziness in there, that area. Sorry, I'm short. You could have reached it without having to jump up and down like I just did. But you know what I'm talking about. Short sucks, I'm telling you. Are we good? Good. So the first layer. I love this part about the sun because it's really weird. Okay? So the first layer is called the photosphere. It's the part that we actually see. It is closest to the inner layers. All right? There are still two more layers on top of this, but we don't see those two layers. We see this layer. It's like plastic wrap. You could see what's in there, and you don't always see the plastic wrap. The temperature here is only about, I love when I say only about, and then I do thousands or millions of degrees, right? The temperature here is only about 12,100 degrees Fahrenheit or 6,700 degrees Celsius. This mask is making me crazy today. I'm going to have to switch it out. This is where all the light from the sun that we get, that blazing, beautiful light, this is where it comes from. Okay? The next layer, by the way, in our little picture, this part here is what we actually see, the photosphere. Okay? Now we're moving out to this part, which is the chromosphere. The chromosphere gets its energy, obviously, from the photosphere, and its temperature is a little bit higher. No, it isn't. No, wait. Yeah, no. A little bit lower, sorry. No, temperature's higher, thickness is lower. You guys, it's been a morning, I'm sorry. It's, compared to the other layers, it's pretty thin. It's only about 1,200 miles wide, thick. But its temperature is between 7,232 degrees and 18,032 degrees Fahrenheit. Maybe that's why the photosphere isn't so cold, so hot. Maybe the chromosphere takes all the heat from it. Huh. A good thought. Now, the chromosphere is kind of the cool part. This is where all the fun stuff happens. This is where you start to get like rushes of gas pushing up through there, and you'll get all the surface features, which we're going to talk about, which are beautiful, but at the same time, you kind of go, oh, I don't want those to happen because those can hurt us, but they're really pretty. You know what I'm talking about, right? Have you ever had something that you go, oh, that's really pretty, I want to touch it? No, don't touch that. That would be bad, right? These jets can go up to 6,200 miles into the or go that high. I mean, not into. They can go 6,200 miles up. That's like twice the width of the United States. So that would be like driving from New York to California and then New York to California again. Okay? We can't see the chromosphere. We can see those jets, but we can't see the chromosphere unless you have special lenses. And if you have those special lenses, then you can see that orange around the outside of the yellow that we had before? That orange is the chromosphere. Okay, and it's all those gases just rolling and moving around. And then the last layer we definitely can't see. The only time we can see that is when there's an eclipse. And it's called the corona. It's the outermost layer. It can only be seen, as I said just a minute ago, it can only be seen during an eclipse or if you have a really special lens on your camera or on your telescope. Oh, and by the way, you know when somebody says you can only see it during an eclipse, and then what do they say right after that? Don't ever do what? Don't ever look at the sun during an eclipse. Well, how am I supposed to see the corona if I can't look at the sun? Come on. Just don't do it. Just don't do it. Just don't do it. Temperature here. That's not in the thousands anymore, by the way. Did you notice that? That's 3,600,000 or up to 9 million Fahrenheit or 2 million to 5 million Celsius. It's toasty. I think the coronas are really pretty. And sometimes, don't tell anybody, sometimes I look at the sun during an eclipse. I know. I don't look long. It's like if you do one of these, you go, okay, not looking, not looking, not looking, not looking, not looking. Oh, that's really pretty. Nope, not looking, not looking, not looking. Right? Sometimes you just have to. Again, the corona, it's going to extend millions of miles into space. Are you breathing? Yes, okay. I'm just waiting, wondering if it's going to be good. Are we good? Okay, now these are kind of the fun parts. These are what actually happens on the surface of the sun that makes it kind of weird. Okay? We have something called sunspots. These spots are cooler, darker spots on the surface of the sun. They're those places like that. Okay? All those dark places are called sunspots. And they happen on the photosphere. And remember, the photosphere is the part of the sun that we see. So these happen down where we can actually see them. Sorry. And they are caused when the magnetic field, you get these loops. Will you stop? Well, put your mouse down, Cindy. When you get loops of the magnetic field that break through the chromosphere, or they come from the middle of the sun, not the chromosphere. They come up through and they kind of like punch holes, okay? Because it messes up as these gases come from down here, and with the magnetic field, it messes up the transfer of heat. And as it messes up that transfer of heat, things start to get cold. Duh, right? So as things start to get cold, you get this dark area because the hotter things are. You guys, I'm sure that you have at some point played with something where it got really, really hot and you could see that it got brighter and brighter and brighter. Ever played with metal that you've done that with, right? Oh, this is so much better, by the way. Okay? Well, then as it cools down, it starts to get darker again. Well, it's the same way with the sun. Those dark spots is because it has started to cool down. And what happens is that sometimes, well, you guys, I hate it when I can't remember what I put in a presentation. I'm sorry. Because I was going to talk about these. But we're not there yet. Notice if you look at these, sunspots almost always happen in pairs. I need my little step stool instead of. See right there? There's two of them here. There's two of them up there. There's two of them. And over here, there's two. They're almost always in pairs. That's because what happens is you get these little arches, which we're going to talk about in a minute, that will erupt from one place, and then they come back down into the surface at another place. And so you get these two dark spots of coldness. There is an 11-year cycle to these sunspots, which I don't know who spent 11 years studying that, but they did. And what they noticed is that you'll start out with this small number of sunspots, and then the next year there will be more, and the next year there will be more, and the next year there will be more, until about 5.5 years. And then it starts getting smaller again until there's just this little number. And then it'll start building back up. And it's always doing that big fluctuation, but it's about an 11-year cycle that it does it. And by the way, it says minimum number. I don't know what that minimum number is. I just know it's not very many. I think these are so cool. These are called solar prominences. And it happens when that plasma, that loop, remember we were just talking about the loop that the magnetic field makes? When that loop has plasma flowing in it, it lights up and it glows. And it's called a solar prominence. So I think they are so pretty. I know I'm weird, I can't help it. These can reach thousands of miles into the air, and they can last anywhere from a few days to a few months or several months. And it'll just be this glowing arc of plasma that is just shooting up into the air and then coming back down on the sun. Now sometimes those arches, see how that's not a complete arch right there? See how you got that break right there? Sometimes there's just a little bit too much energy in that arch, and that arch breaks. And when that loop, that arch breaks, we get what's called a solar flare. As long as they're little ones like this, we don't worry about them too much. But sometimes they can get massive. And what these really are is they're explosions. Because when that breaks, it creates this explosion. And it's sometimes, I talk about them little explosions, but that's little for the sun. For us, they would be mega explosions, right? But it releases this big amount of energy. And if that energy is too big, it can turn into what's called a coronal mass ejection. These we worry about. Because coronal mass ejections create the solar winds. They release big particles of energy that travel through space at ridiculously fast speeds. Okay, so what, Mrs. Skipper? So it's energy and it's moving around in the universe. Duh. I mean, come on. We want that energy, right? Well, we want a little bit of energy. We really don't want that much. If you look here, this is like our magnetic field. This is Earth right there. That little teeny tiny dot right there, that's Earth. And this is our magnetic field, and this orange stuff is the solar flare. And the solar flare can actually push through our magnetic field, and it can disrupt our magnetic field. And when it does that, it will damage spacecraft. If we have spacecraft that are out there and astronauts on the spacecraft, they don't have a lot of shielding. They don't have, a magnetic field around them. They don't have this magnetic barrier to protect them from that radiation. So it can hurt our spacecraft, it can hurt our astronauts, and it can break through our magnetic field enough that it can actually cause even more skin cancers than normal with people that are outside. And it can hurt people too. It has actually been known to knock out power grids. So like an entire city will go dark because their power will just go out because of these solar winds. Cell phone reception, forget about it. Forget about it, right? No, it's not. The solar winds, all that energy can knock that out. Our radios, our satellites, all that kind of stuff, it can mess a lot with communication. Questions? That's it. Look, I'm scrolling. Nothing more today. Are we good? Give me just a minute to stop the recording, and then I'll ask you if you need to go back and fill any in. Oh, stop. Where is it? There it is.